This video will extend our knowledge of vectors to a second application involving bearing. Okay, a bearing is a direction that measures the acute angle that a path or line of sight makes with a fixed north-south line. And air navigation bearings are measured in degrees clockwise from north. Okay, so we have an airplane that is traveling at a fixed attitude with a negligible wind factor. The airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees. I drew a picture of this. There's the plane there. They didn't really make sense because they just threw the 120 on there. I want to show you where that comes from. Remember, bearing are measured in degrees clockwise from north, like stated above. So if we look at my first picture there, I put the V1 there. I wrote down my magnitude because they told me that it's a speed of 500 miles per hour. And then I did 330 degrees from north and clockwise. Okay, so remember anytime, and I said this in the last video, but anytime I'm going to use my angle and I don't want to think about trig, I want to think about it from here. Always the standard angle. Okay, I do know this though. This is 30 degrees, just based on 330s all the way around, so or 330s to V1 and then 30 more to 360. So that means this angle here is the 90 degrees in quadrant 1 plus 30. That gives me the 120 degrees. Now, if I want to keep my trig straight and not have to think about it, I want to use that angle, not 330. You can use 330. You're just going to have to be careful with the signs, S-I-G-N, the signs, not S-I-N. Okay, so I am going to, I forgot to mention this, and we should. Let's read the rest of the problem. As the airplane reaches a certain point, it encounters wind with velocity of 70 miles per hour in the direction of north, 45 degrees east. That means 45 degrees east of north. And that's in this figure here. You can see that V2 hitting the airplane there. What are the resultant speed and direction of the airplane? Okay, so we know that if I want V, that's going to be my resultant airplane vector, that I just add V1, which is the path of the plane, plus V2, which is the wind. So I need to find a V1 and a V2. So V1, in this case, if I use this, and this is using the trig involved, this is the, to find my I component, it's going to be 500 cosine 120 I, and then plus 500 sine 120 k, j, sorry. K is our z or z component. So, okay, let me scoot this over. Okay, we have that for V1. Let's go ahead and get a number for it so we don't have to do it later, or decimals meaning. Okay, so the first one, cosine of 120 times 500, I'm going to get a negative 250 I. This makes sense. That's the x component. It's going to the left. Okay, so it should be negative. Plus, okay, 433.013J. That makes sense too. The plane is going up, so the y direction should be positive. All right, let's do V2 now. Now, we want this same thing. They gave me that this angle here was 45 degrees. So if that's the case, then this angle here is also 45 degrees. This is going to make this pretty easy. Cosine 70 of cosine of 45 I plus 70 of sine 45 J. That's just using right triangle trig, but I'm just using the patterns that we've seen. I'm hoping you guys are used to that at this point, maybe some physics or maybe something along those lines that you guys have seen, how to get your x and y components of a vector, a line really. But I hope you have that down at this point because it does make it easier if you're not having to think about the triangle every time. It's always magnitude times, for x it's cosine, and for y it's sine of the proper angle that you got to find. Right, V2 now in decimals. V2 is 49.497 I plus 49, and this make their sine 45, cosine 45, they're the same thing, so I get the same 497J. This makes sense. It's 45 degree angle, pushing in the same direction, or pushing with the same magnitude. Makes sense that those are exactly the same. So to find V, I just add them up. So adding those things, I'm going to go ahead and do that for us. I got negative 200.503 I, this is a vector, plus, okay, if I add the other ones, I get 482.51 J. Right, remember this is not the resultant speed. This is a vector describing the resultant of the airplane. Which way is it going? If I want to find the speed, I find the magnitude. Right, you square each one, add them together. You roughly get, I'm going to go ahead and do that. We get roughly 522.51 miles per hour. I'd recommend you run that through the formula and match it. Not just write down what I wrote down. Square both of those, add them together, and take the square root. Okay, if I need to find the angle, we're going to use trig here. We have an x and a y, and I would really like to find the angle that's in between, that's there. We can use tangent. If I have x and y, tangent of an angle is y over x. So we get 482.51 over negative 200.503. So theta is equal to the inverse tangent of that thing. I'm not going to rewrite it. I'm just going to do that. And that is roughly 67.435 degrees. Okay, but that's not the theta they want. Let's call this theta 1. This was this theta. So to find theta, I'm going to take 180 and I'm going to minus that 67.435 degrees. And then let me grab my calculator. 180 minus 67.435. The angle is 112.565 degrees. You should do a rational check. What I mean by that is the original angle up here was 120. And if wind pushes it over, it makes sense that it would be a little smaller. It'd be a 112. So you should definitely check that rationally, because if it doesn't make sense, then what are we doing, right? So make sure to check that. These are done very similarly every single time. There is a problem that I like to give sometimes about a traffic light, stuff like that. Anything suspending with forces, anything pulling, any kind of problems like that, just go work them.